Hello, welcome to the second set of short video series on probability theory. In this series, we will talk about random variables. So let us start with some definitions. So let us define the random variable. A random variable basically represents a process in which we have an experiment, that is basically you conduct a physical experiment or basically take observations, and then we assign probability measures to the outcomes of these experiments. That is, for example, if you toss a coin, the possible outcomes are either heads or tails, but in order to study them using mathematics, we have to assign some values to these outcomes. For example, you can assign 0 to heads and 1 to tails. So the outcomes, heads and tails, form the sample space, and the values assigned to these outcomes, that is 0 and 1, form the basically represent the random variable that is assigned to these outcomes. So usually random variable is represented by a capital X or a capital character, and a realization of this random variable is represented by small x, and the actual outcomes of the experiment S are related to these realizations small x, usually by a complex function which is difficult to analyze or determine deterministically. So examples of random variables are a number of phone calls a person can get in a day, or a noise level in a radio receiver. Any measurement that we can take in a real life or a real world situation can be designed as can be modeled as a random variable. For example, speed of a car on a highway. Another example is distance between two cars on a highway. Another common everyday example is amount of traffic going through, for example, an internet router in your house. All these observations or all these measurements can be modeled as random variables. So let us define a discrete random variable. A random variable is discrete only if its values are countable. That is, for example, if it takes values from 1 to, if it takes natural numbers 1, 2, 3 and so on. Note that the random variable can be greater than 1. There is no restriction on the value of the random variable itself, but the probability of the random variable is always going to be between 0 and 1. So a discrete random variable can belong to a set x1, set Sx, where the elements are x1, x2, x3, that is their values are known, that is they are countable, but the total number of possible values can be infinite. A good example for discrete random variable is the number assigned to the numerical value assigned to the output of a coin toss experiment. That is, the sample space consists of heads and tails, but the random variable t that numerically represents these outcomes as, for example, 0 for heads, 1 for tails, consists of the set st, or it composes the set st with the elements 0 and 1. So this random variable t is a discrete random variable. Another example is population size, for example, in a city or a town or a country. So the population size is a discrete random variable. There can not be anything like 4.5 people or 10.5 people. There are always, here the total population is also integer valued. So it's a discrete random variable that takes only integer values. In other words, the random variable is definitely countable. And next definition is finite random variable. If the total set of possible values for the random variable is finite, that is, it has limits x1 and xn, and it belongs to the set x1, x2, set consisting of the numbers from x1 to xn, then we call it a finite random variable. For example, consider the grades a student gets in a class. The possible grades are from A, B, C, D, F, that is from the sample space S, which has 5 possibilities, that is A, B, C, D and F. And sometimes numerical values are assigned to this sample space, the outcomes in the sample space. For example, we can denote this random variable as G, which takes values from the set Sg with values from 0 to 4, where 0 corresponds to F and 4 corresponds to A, respectively. Now let us look at the definition of probability mass function. The probability mass function is basically the probability assigned to discrete random variables. That is, it is a probability that a random variable is equal to one of the discrete realizations. For example, in a coin toss experiment, we have two possible outcomes. Now we can assign a value 0 for the first outcome, that is heads, and a value 1 for the second outcome, that is tails. And then if the probability of the first outcome, that is heads, is p, then the probability of the second outcome is 1 minus p. Then the probability mass function in this case has two values, that is p for t equal to 0 and 1 minus p for t equal to 1. This probability mass function has value of 0 for t less than 0 and for t between 0 and 1 and also for t greater than 1. So basically probability mass function has only values or non-zero values at the discrete realizations of this random variable. In the second experiment, when you roll a die, we have 6 possible outcomes. So we can assign a value 1 for the first outcome and a value 2 for the second outcome and so on up to value 6. That is, we have a range consisting of 6 values, that is 1 to 6. The probability mass function is equal to 1 by 6 at each of these 6 values, since especially when you assume that the die is unbiased. The probability mass function does not have any value or its value is equal to 0 for d not equal to one of these 6 values. Now let us look at the properties of these probability mass functions. Essentially, the probability mass function has same properties as the probability of outcomes learned in the previous chapter. That is, the first property is probability mass function is always a non-negative function. That is, probability that a random variable is assigned to one of its realizations or values in the range is always greater than or equal to 0. The sum of the probability mass function for a random variable over all possible realizations within the range is always going to be 1. In other words, the total probability of a random variable is always going to be 1. And final property is that the probability of an event is equal to the sum of the probabilities or probability mass function of a individual realizations of the random variable defining that event. That is, for example, for an event B, it defines a subset of the sample space. The probability of event B is equal to the sum of the probability mass function of a random variable whose range is equal to or whose range corresponds to the event B. So let us look at some examples illustrating these 3 properties. So consider our experiment, roll a dice and see the 2 outcomes and note the values. So the sample space consists of 36 possible outcomes, that is from 1, 1, 2 to 6, 6. So there are 36 outcomes. Now consider a random variable x, that is a capital X, whose range is Sx, and where we assign individual numbers or countable numbers from 1 to 36 to each of the possible outcomes in the sample space. So the range has the values 1 to 36, or the natural numbers 1 to 36. So we can clearly see that the probability mass function is always going to be equal to 1 by 36 for a unbiased dice. So it's a uniform probability mass function, and we can clearly see that it is always greater than 0. So this is the first property. The second property is the total probability of the range, the sum of the probability mass function over the whole range, that is Sx, is equal to basically summation of 1 by 36 times. That is equal to 1. So this is the second property. And now let us define an event B that has 1 in its first value. That is the first of the 2 dice. The first die always has a value 1. So in this event, there are 6 possible outcomes in this event. So now let us define the range corresponding to this event. It has the values 1 to 6. So this range is a subset of the larger range Sx, and we can clearly see that the probability of the event B, which is obviously equal to 6 by 36, that is equal to 1 by 6, is also equal to the sum of the probability mass function where the small x has the values 1 to 6. So the sum is equal to 6 times 1 by 36, which is equal to 1 by 6. Hence the probability of an event, or basically collection of realizations, is equal to the sum of the probabilities of individual realizations. Thanks for watching.